Okay, so this is a graph between the electron density in the conduction band, that is electron concentration in the conduction band, that is the number of electrons per unit volume. That's why you have its unit as per centimeter cube. So on the y-axis we have the electron concentration, and on the x-axis we have the temperature in Kelvin. Above we have temperature in degree centigrade. So we start from 0 Kelvin. So 0 Kelvin means all the electrons, and remember it is N-type semiconductor with the doping concentration, donor concentration equal to 10 to the power 15 donor atoms per centimeter cube in silicon semiconductor. So when the temperature is 0 Kelvin, there is no electron in the conduction band. That's why at 0 Kelvin the electron concentration is 0. When we start increasing the temperature, so the donor atoms require only few millielectron volt of energy. Few millielectron volt. This is not very great energy. So only few millielectron volt of energy is required. And when the temperature provides this much energy, so the donor atoms starts getting ionized, means they donate electrons to the conduction band. So the electron concentration in the conduction band increases. As the temperature is increasing, more and more donor atoms get ionized. They donate their electrons to the conduction band. So, and this increase is exponential. This increase is exponential. It is given by some exponential term. So the electron concentration in the conduction band increases exponentially as the temperature increases. Now we reach at this point. At this point, all the donor atoms are ionized, means each donor atom has now become ion, and this donor atom has contributed one electron to the conduction band. So what is the concentration of electrons in the conduction band at this particular temperature, around 150 Kelvin or so? These all electrons are donated by donor atoms. This region is known as freeze out region. Now, if we increase the temperature beyond this temperature, beyond 150 Kelvin, so what is going to happen? Because all the donors have donated their fifth valence electrons, but the thermal energy is not sufficient to break a covalent bond. Therefore, the concentration of electrons in the conduction band remains constant. It does not change because electrons are not coming from anywhere. Electrons are not coming from anywhere, and the electron concentration remains constant. Now, when the temperature is sufficiently high, around 450 Kelvin, the thermal energy is sufficient so that it will break a silicon-silicon covalent bond. This means that the electron now can jump from the valence band to the conduction band, and the temperature is increasing, more and more covalent bonds will break, and therefore the electron concentration in the conduction band again starts increasing. So in this region, the electron concentration is increasing due to the breaking of covalent bonds. That's why it is analogous to, or it is similar to the intrinsic region. Okay, so as the temperature is increasing, the electron concentration increases like this. So, and this is for the dashed line. It is for an intrinsic semiconductor in which we have not doped anything. So you see up to 400 Kelvin, the electron concentration in the conduction band is 0 because the thermal energy is not sufficient to break the covalent bond. If it is a silicon semiconductor, then we require 1.1 electron volt of energy to break the silicon-silicon covalent bond. But when the temperature is around 450 Kelvin, so the covalent bonds start breaking or start rupturing, and the electrons are free to roam around in the crystal. Means the electron makes a transition from the valence band to the conduction band, and with the increase of temperature, the electron concentration in the conduction band increases. So you can see in this region, the intrinsic as well as the extrinsic semiconductor, they behave more or less the same way. Remember, this is only the electron concentration behavior. If you want to see how the conductivity or resistivity of the semiconductor will vary, it is the conductivity will depends upon the electron concentration times the electronic charge times the mobility of electron. So mobility of electron also depends upon temperature. It behaves differently in different regions. So when we multiply the variation of mobility with temperature with electron concentration with temperature variation, so we will get the total variation of conductivity as a function of temperature for semiconductor. And you have seen this graph in your experimental 4-probe method, where the resistivity increases exponentially with the decrease in temperature, and from that graph you calculated the band gap of semiconductor. So is it okay, Somen?
Yes, sir.
All right. So I told you can follow the book Electronic Principles, Principle of Electronic Materials and Device by Safa or Kasab, and its soft copy is available on the net, and its hard copy is also available in the library, central library. The same behavior will be for p-type semiconductor. Nothing is going to change. Initially the acceptor atoms will start ionizing, means the electron will jump from the nearby covalent bond and the acceptor atoms become negatively charged. So the whole concentration in the valence band will increase. Then there is a temperature at which all the acceptor ions are ionized. They become negatively charged, and after that the whole concentration in the valence band will not increase. But again, the temperature is so high that it will break the covalent bond, and more electron hole pair will be generated. So whole concentration will increase in the valence band. Same behavior for N-type and P-type semiconductor. All right. So remember that we discussed this mass action law, in which the product of electron concentration in the conduction band with the whole concentration in the valence band is equal to Ni square. Ni is the intrinsic carrier concentration. I here represent intrinsic. So this is known as mass action law. And if we see the three type of energy band diagram of three semiconductor, one is intrinsic semiconductor, the other one is N-type semiconductor, and the last one is P-type semiconductor, we can see that in intrinsic semiconductor, the electron concentration in the conduction band is equal to the whole concentration in the valence band. The same number of electron hole pairs are generated, that's why their number is equal. And you see, if we assume that the effective mass of electron and hole, they are same, so the Fermi level, it is shown by EFI, intrinsic Fermi level. It lies exactly at the center of this band gap. It is shown by dotted line because it is not a real energy level, because no real energy level can exist here. Had it been a real energy level, it should have been shown by a complete solid line, but it is not so. It is not so. So the difference between the Fermi level and the top of valence band, top of conduction band, it is known as the work function. The energy required to raise the electron from the Fermi level to the vacuum level. The top of conduction band represents the vacuum level. So, but this definition is valid for metals in which we have electrons at the Fermi level. In case of semiconductor, we don't have any electron at the Fermi level, so this quantity is not so important. It is just to tell you that this much is the work function for semiconductor. The important quantity for semiconductor is this chi. It is electron affinity. So it is the difference between the bottom of conduction band to the vacuum level. So this is chi, because actual electrons are present here. So how much energy is required to take out electron from the bottom of conduction band to the vacuum level, it is defined as electron affinity. So in case of semiconductor, this quantity electron affinity is important. For N-type semiconductor, the Fermi level is between EC and you have donor levels here below EFN. So in case of N-type semiconductor, please remember it is very important concept. The Fermi level is between the bottom of conduction band and the donor levels. Donor levels are not shown here, but they are at this position where we are moving the cursor. So in N-type semiconductor, I again repeat, the Fermi level is in between the bottom of conduction band and the donor levels. So now in this case,
sir, is the donor level is on the halfway between EC and EV?
they are not at EF is half level. EF is at half level. Donor level. Can you see the cursor?
Yes, sir. Yes, sir.
So the donor levels are somewhere here. Donor levels are somewhere here. Fermi level will be between donor levels and the bottom of conduction band. Similarly, for P-type semiconductor, so before that, you see in the case, the work function in the case of N-type semiconductor is represented by phi N. So N here represent it is N-type semiconductor. And you can see that in N-type semiconductor, we have large number of electrons in the conduction band. Their concentration is large and the hole concentration is very small. Hole concentration is very small. So in N-type semiconductor, we can generate large number of electrons without increasing the hole concentration. For intrinsic semiconductor, if you want to increase the hole concentration, the electron and hole concentration would be the same because electron and holes are generated in pair. But here we have the donor atoms which will donate extra electrons. So these are the electrons donated by donor atoms. That's why we have the hole concentration very small. In case of P-type semiconductor, we have very less number of electrons that comes from the breaking of covalent bonds, very less number of electrons at normal temperatures, but we have very large number of holes. And again, the Fermi level in P-type semiconductor will be between the top of valence band and the acceptor energy levels. Acceptor energy. So you can consider this to be acceptor energy level. So the Fermi level is in between the valence top of valence band and the acceptor level. In this case, the work function is denoted by phi p. So mass action law will hold good. Mass action law will hold good for intrinsic as well as N-type and P-type semiconductor. So this is the table that, yes.
Sir, if we are interested in affinity, then why are we using the word work function in case of semiconductors?
This is just to differentiate. So, for example, if we want to make a p-n junction device, this is p-type n-type semiconductor. This is p-type semiconductor. So the difference of the work function will tell how much is the difference in the Fermi level. I told you under thermal equilibrium, there will be one Fermi function. There will be one Fermi level across the whole device. So, but you see here, there is a difference in the Fermi level. So the difference of Fermi level is calculated if we know what is the work function for n-type semiconductor, what is the work function for p-type semiconductor. So this difference phi p minus phi n is equal to the difference in Fermi level. So we have to reduce this difference if we want to have the one Fermi level across the p-n junction. Okay?
Yes, sir.
Sir,
Yes.
sir, is electron affinity same for all these three types of semiconductor?
No, how can electron, if it will depend, where is the Fermi level located. If from the figure, it would be same, because all the levels of bottom of conduction band, they are at the same value, but for different semiconductor, it would be different. Okay.
Okay, sir.
So in this table, various data for several semiconductors are given. So for example, we have germanium, silicon, indium phosphide, gallium arsenide, and aluminum arsenide semiconductors. So inside the bracket, something is written Di. So Di is this represents the diamond structure. I told you germanium and silicon, they crystallize in diamond structure, and we know what is the diamond structure. It is two interpenetrating FCC lattice which are displaced at quarter position with respect to the other unit cell. So Di here represents the diamond structure. So germanium and silicon possess diamond structure, and A is lattice constant. That is because the structure is cubic, so the length of the unit cell in all the dimensions would be the same, and it is 5.65 angstrom for germanium, 5.431 for silicon. For indium phosphide, indium phosphide, gallium arsenide, and aluminum arsenide, all these are binary semiconductors because they have two elements in them. So they possess zinc blende structure, and zinc blende structure is also analogous to diamond structure, but in this structure the atoms are different. One is gallium, other is arsenic. That's why it is zinc blende structure. Otherwise, the structure is more or less diamond, in which one atom is located at the corner of the unit cell and the other atom is located at quarter position. I hope you remember the diamond structure. So band gap for germanium, you know, it is around 0.7 electron volt. For silicon, it is 1.1 electron volt, and for indium phosphide, it is 1.35 electron volt. For gallium arsenide, it is 1.42 electron volt. For aluminum arsenide, it is 2.17 electron volt. And in the bracket, some numbers are written, some like ID. I here represents it is indirect band semiconductor. I will tell you the concept of direct and indirect band semiconductor. So where you find this letter I, it represents it is indirect band semiconductor. So germanium and silicon, they are indirect band semiconductor, and all other binary semiconductors, they are the direct band semiconductor. So except this aluminum arsenide, it is also indirect band semiconductor. I told you that for making LED, light emitting diodes and semiconductor lasers, only the direct band semiconductors are used, not the indirect band semiconductors. The next column is the electron affinity value, and it is between 3.50 to 4.5 electron volt for these semiconductors. Next two columns are the effective density of states at the conduction band edge, NC, and the effective density of states at the valence band edge. So you see the order is from 10 to the power 17 to 10 to the power 19 per centimeter cube. It is very, very high. You please remember this order, because on the next slide we will discuss something that is related with this order. So we will compare the electron concentration in the conduction band with this order, and then you need to remember it varies from 10 to the power 17 to 10 to the power 19. Similarly, in the valence band, the effective density of states at the valence band edge is 10 to the power, it varies from 10 to the power 18 to 10 to the power 19, and this is electron concentration, intrinsic electron concentration. Germanium has the lowest band gap, so it has the highest electron concentration in the conduction band. Then we have silicon, 1 into 10 to the power 10, indium phosphide, 3 into 10 to the power 7, and gallium arsenide, 2.1 into 10 to the power 6. So then the next column is about the dielectric constant. So these are the values for dielectric constant, and the next column is about the electron mobility, and you see the unit is centimeter square per volt second. And the last column is for the whole mobility in the valence band. So if you compare these, you can see that gallium arsenide has the highest electron mobility, 8500 centimeter square per volt second, and the whole mobility is smaller. That's why I told you that whenever we require very fast switching applications or very fast speed, then we use gallium arsenide, because here the electron mobility is very, very high. So the lower table, it shows the different the donor energy levels in electron volt, and you can convert it into milli electron volt for different type of donor dopants, and the same thing for acceptors. So for example, if in silicon we dope phosphorus, it will make it n-type semiconductor, and the donor ionization energy for phosphorus is 45 milli electron volt. For arsenic, it is 54 milli electron volt. For antimony, it is 39 milli electron volt. Similarly, for acceptors, if we dope any element from group third like boron, aluminium, or gallium in silicon, then these are the energy only in few milli electron volt that is required to ionize the acceptor levels. On this slide, we have different impurities doped in silicon semiconductor. You can see it is silicon with band gap equal to 1.1 electron volt. So if you are doping like boron, aluminium, gallium, indium, palladium, so they make these are the numbers, the mathematical numbers over these bars represent their ionization energy in electron volt. So you can see that now the levels which are very close to the valence band, they are known as the shallow levels, and the levels which are very far from the valence band, they are known as the at the deep levels. So, for example, D here, D represents here donor, but you can see here the difference is very, very large. It is 0.3 electron volt. So such levels are known as deep levels. Deep levels. Similarly, if we have the doping of antimony, phosphorus, arsenic, they will make the silicon semiconductor as N-type semiconductor, and their ionization energy are given like this. If we substitute titanium, so its energy level would be like this. For carbon, it is like this, 0.25 like this. So this is deep level, this is deep level, which is very far from the either the top of valence band or bottom of conduction band. So we have two type of impurity levels in the band gap. One is the shallow levels whose difference or whose energy is very small, and the other one is the deep levels who require large amount of energy to get ionized. So if you compare antimony with this, you see it requires only 39 milli electron volt to ionize this antimony donor atom. But if it is present here, for example, here D represents here donor, A represents acceptor. So it requires 290 milli electron volt of energy to ionize this atom. I hope it is clear to you. So now we differentiate or we discuss the two terms. One is the non-degenerate semiconductor, and next we will discuss about degenerate semiconductor. So now I want your focus or I want you to recall the order that I told you to remember. The effective density of states at the conduction band edge is of the order of 10 to the power 18 to 10 to the power 19. So when the electron or hole concentration in the conduction band and valence band is much lower than the effective density of states in the conduction band or the valence band, the Fermi level is at least 3 kBt above the top of valence band or 3 kBt below the valence band. For such cases, the semiconductor is referred to as a non-degenerate semiconductor. So I told you the effective density of state is 10 to the power 18 to 10 to the power 19 per centimeter cube. If the donor or acceptor concentration is like 10 to the power 14 or 10 to the power 15 per centimeter cube, which is much smaller than 10 to the power 18 or 10 to the power 19, then the Fermi level will be at least 3 kBt above the top of valence band or 3 kBt below the 3 kBt below the conduction band, and such levels are known as shallow donor levels or shallow acceptor levels, and we require very less amount of energy to ionize them. And if we have sufficient temperature, very close to room temperature, all the acceptors or all the donors can be ionized. This process is known as complete ionization. So such semiconductor in which the donor or acceptor concentration is much smaller than the effective density of states, then such semiconductors are known as non-degenerate semiconductor. Non-degenerate semiconductor. So it is like this. There the concentration of donors or acceptors is not too high that their wave function will start overlapping with each other. They are lying very far from each other. There will not be any interaction between the donor or acceptor levels among themselves. That's why they are known as non-degenerate semiconductors. Non-degenerate semiconductors. Okay. So when we have complete ionization, means if we have the N-type semiconductor and all the donor atoms are ionized, so the electron concentration in the conduction band is equal to the donor concentration, that is Nd. So in this diagram, you can see that we have this Ed represents the donor energy levels, and you can see that each donor atom has contributed one electron to the conduction band. It has donated one electron to the conduction band. So it is the process of complete ionization, where all the donor atoms are completely ionized. All the donor atoms are completely ionized. Similarly, here you see the acceptor energy levels, in which all the acceptor atoms, they have accepted one electrons from the valence band, and all the acceptor levels are ionized. In such case, for this B diagram, the whole concentration in valence band is equal to the acceptor concentration. P is equal to Na. Now, I told you that for N-type semiconductor, the Fermi level is in between the bottom of conduction band and the donor levels. So the difference between the conduction band and the Fermi level, we can write Fn here to denote that it is the Fermi level for N-type semiconductor. So Ec minus Ef is equal to kBt. Kb here k is written, but it is kb Boltzmann constant, times T natural log of the effective density of states at conduction band is divided by Nd, that is donor concentration. So similarly, the Fermi level for p-type semiconductor, EFP minus EV is equal to kBt natural log Nv over Na. Now, if you see, if Nd or Na is higher, means we keep on increasing the donor and acceptor concentration. So this number will, the Nd and Na, they are in the denominator. So if the denominator is increasing, the ratio will increase or decrease?
Decrease.
It will decrease. So this number is going to decrease. So, and on the left hand side we have the difference Ec minus Ef. Since this right hand side number is decreasing, so the difference between the conduction band bottom and the Fermi level for N-type semiconductor will decrease. Similarly, if we keep on increasing the acceptor concentration, the difference between the Fermi level of p-type semiconductor and the top of valence band will decrease. Means the Fermi level for N-type semiconductor will move closer to the conduction band, and the Fermi level for p-type semiconductor will move closer to the top of valence band. So this is the diagram for N-type semiconductor, in which we have the donor levels shown by Ed. We have conduction band, valence band. There are several electrons in the conduction band. Next, we plot the density of states, and density of states for a three-dimensional semiconductor, it varies. It is proportional to under root of E. It varies proportional, it is proportional to under root of energy. That's why you see parabola. For hole it goes like this, for electron like this. And this is the density of states. It is not too high for the donor concentration, donor atoms. And this is the Fermi-Dirac distribution function. And in order to calculate the concentration of electron in the conduction band or hole in the valence band, what we need to do? We need to multiply the Fermi-Dirac distribution function with this density of states, and we will get this graph. So area under this curve will show or will tell the electron concentration in the conduction band. And it is, since it is n-type semiconductor, the electrons are given by the donor atoms. So the electron concentration is very large, and you can see the area under the curve is very large. Here you see the hole concentration is very small, so area under this curve is very small. But still, this relation holds good, that the product of electron concentration in the conduction band with the hole concentration in the valence band is equal to Ni square. Now, it may happen that we may have both acceptor as well as donor levels in any particular semiconductor. So if both donor and acceptor impurities are present simultaneously, then, and we want to check whether it is n-type semiconductor or it is p-type semiconductor, so the impurity that is present in greater concentration, it determines the type of semiconductor, whether it is n-type semiconductor or whether it is p-type semiconductor. So if, for example, if the donor levels or donor doping is more than the acceptor doping, then naturally it will be n-type semiconductor. However, if the acceptor concentration is greater than the donor concentration, then it will be p-type semiconductor. Still, the total semiconductor will be electrically neutral. It will be electrically neutral. So electrically neutral condition will be satisfied. Electron is negatively charged, and the acceptor levels, when they accept electrons from the valence band, they are also negatively charged. So the total negative charge is equal to the total positive charge. So N plus Na is equal to P plus Nd. Na and Nd here, we can write here minus sign in order to differentiate it from the neutral acceptor atom. We can put minus here and we can put plus here, because now this shows that it has negative charge and this shows it has positive charge. So we have this equation in between, so we can write it N minus P is equal to Nd minus Na. And the other equation between N and P, we have N into P is equal to Ni square. So we have two equations, and from the two equations, we can calculate N in terms of Nd and Na. It would be given by 1 by 2 times Nd minus Na plus under root Nd minus Na whole square plus 4 Ni square. And similarly, the whole concentration is given by this. And if we know the electron concentration, we can calculate what is the whole concentration. If we know what is the whole concentration, we can calculate what is the electron concentration in the conduction band. So I don't know why it is. So magnitude of the net impurity concentration, that is Nd minus Na, is larger than the intrinsic carrier concentration. Therefore, the relationship can be simplified to N. If the donor concentration is greater than the acceptor concentration, the total electron concentration in the material will be N-type semiconductor, and the electron concentration in the conduction band is approximately equal to the difference Nd minus Na, if the donor concentration is greater than the acceptor concentration. However, if the acceptor concentration is greater than the donor concentration, the overall semiconductor will be p-type, and the whole concentration would be equal to their difference, Na minus Nd. All right. So next, And final topic of the day, we discuss about the variation of Fermi level with two things. One is if we increase the acceptor or donor concentration, and the second thing is if we increase the temperature. So here you see this graph when the donor concentration is very small, 10 to the power 12 per centimeter cube, 10 to the power 12 per centimeter cube. The donor concentration is very small. So the Fermi level is very close to the conduction band, But when we increase the temperature, Fermi level will start moving down, and at this temperature, the Fermi level will be equal to the intrinsic Fermi level, or the difference in the Fermi level of N-type semiconductor and the intrinsic semiconductor will become zero. That's why you see we started our discussion with this curve. At high temperature, the semiconductor becomes intrinsic. The Fermi level now is at the center of the band gap. Here at this position, the Fermi level is in between the donor level and the bottom of conduction band. It is very close to the conduction band. But as the temperature is increasing, the Fermi level for N-type semiconductor is moving down, and at one particular temperature, it is the same as that of an intrinsic semiconductor. Now, if we increase more donor concentration, you know that we discussed here. If we increase the donor concentration, the difference in the EC and EF, it is smaller. Means the Fermi level moves closer and closer to the bottom of conduction band, or Fermi level moves closer and closer to the top of valence band. Therefore, we require more temperature to make this N-type semiconductor as intrinsic semiconductor. And as the concentration is increasing, you see here the Fermi level is very close to this conduction band, and we require very, very large temperature, If you extrapolate it, it will cut here somewhere around 1000 Kelvin or so. Similarly, I don't know. Okay, so I stop here because many